Okay, so in chapter 16, we looked at inference and statistics about proportions specifically. We're going to be doing the exact same thing in this chapter, but with means. So it'll go a little bit faster because we have some of the foundational ideas in place, and we're just making a transition from proportions to means. So our learning goals, I can explain how the t distributions are different from the standard normal distribution and why it is necessary to use a t distribution when calculating a confidence interval for a population mean. I can state and check the conditions for constructing a confidence interval for a population mean. I can determine critical values using a t distribution, and I can construct and interpret a confidence interval for a population mean. So some of those words were familiar, some of them were new, especially the t distribution stuff. So we'll go ahead and get started with that. So, like I mentioned, in the previous chapter, we've looked at how to generalize data for proportions, but of course, not all data is answered as a yes or a no question, as successes or failures. So in this chapter, we're going to learn how to make confidence intervals with quantitative variables, and so we're going to look at specifically means. So we're going to stop looking at p, population proportions, and try to generalize mu, population means. So just a reminder of the notation, mu, that little funky looking u, is the symbol for the population mean. It's the parameter symbol that we use for the population mean. And then x with the line over it, which is read as x bar, is the sample statistic. It's the sample mean, and we use that to estimate mu. Okay, so for mean and standard deviation, for the mean of a sampling distribution, like say you take a simple random sample, if you take enough of those and you're looking at the sampling distribution, the mean of the sampling distribution should be equal to the mean of the population. And again, this is not dependent on shape. For proportions, it had to be approximately normal. For this, it will not have to be. And then we'll look at what conditions need to be met. And then for the standard deviation of a sampling distribution, as long as certain conditions are met, which we're going to talk about, then for this one, the standard deviation of a sampling distribution will be equal to the population standard deviation divided by the square root of n, your sample size. So, this is, like I said, going to be looking at the same stuff as proportions. So remember, proportions, the estimator of p was p hat. And then we had the formula for the standard deviation, which was p times 1 minus p over n, and taking the root of that. Well, here's our formula for the standard deviation when we're looking at means and not proportions. It's the standard deviation divided by the square root of n. So just knowing when to use which formula. You'll have to use this when you're dealing with means, the other formula, of course, when you're dealing with proportions. So for the shape of a sampling distribution, if the population that you're sampling from is normally distributed, then the sampling distribution will also be normally distributed. That's always true. But when it comes down to it, most population distributions are not normally distributed. So, what is the shape of the sampling distribution of sample means when the population distribution isn't normal? So we're going to look at a new theorem to help us answer that question, and that theorem is the central limit theorem, often abbreviated CLT, central limit theorem. So first off, let's see what happens. It'll kind of help us establish the central limit theorem. So say we're taking taking random samples of salaries and plotting the sample means. Before we look at the distribution of all Major League Baseball salaries from 2016, think about what do you think will be the shape of the distribution? And then what do you think the mean salary is of the Major League Baseball players once we look at these graphs? Okay, so here is the distribution of MLB salaries in 2016. So you can see it is definitely skewed right. You have some lower ends, but then of course you have players who make on the significantly higher end of things. And for this is where the population is not approximately normal. But then what about the shape of the sampling distribution if we take many, many different samples? Okay, for this one, if you look at this, describing the distribution, it's skewed right. How many salaries were in the data set? Well, if we look back for this one, it said there were 862. So you have the summary statistics there. Why does it make sense that the mean is larger than the median? Just a reminder, that always happens when the data set is skewed right. And then what is the standard deviation? The standard deviation was 5.9. And just a reminder of what that tells us that this data set as a whole typically varies from the mean by 5.9. So typically you would expect a salary to vary from the mean by 5.9. So just a reminder of that information. But then for the central limit theorem, let's look at what happens when we have sampling distributions of different size. We're going to look at sample size of 2, 4, 8, 10, all the way up to 30, and pay attention to the shape, the mean, and the standard deviation for each one. And then think about how that compares to the distribution of the entire population of baseball player salaries. Okay, so when we looked at a sample size of 2, and this is a sampling distribution where we took a sample size of 2 for 2,000 samples. The mean is 4.5, which the true mean was, if you recall, 4.3, so a little bit higher. The standard deviation was 5.9. So again, just to compare the shape, when we do sample size of 2, the shape is still skewed right. The mean is slightly higher than what it truly is, and the standard deviation or standard error is way lower. If we do sample sizes of size 4, we still have a right skew. The standard deviation is getting smaller, even 2.8, and the mean has started getting closer to what it really was. If we look at sample size of 8, the mean still relatively close to what it was before. We're now at 4.4. The standard error, which is again an estimate of the standard deviation, is still getting smaller. And while this is skewed right, it's definitely starting to get more normal shaped. Sample size of 10, same thing. The mean is now closer to what it truly is, and the standard error is now gotten even smaller. For a sample size of 15, standard error smaller, and we're getting still less right skewed. Sample size of 20, the standard deviation smaller still, and now we're definitely getting to where it's approximately symmetric. Still a slight skew at the end. There's still a slight right tail. And then once we get to 25, similar picture here. There's still a slight tail, a slight right skew. The mean is closer to what it truly was. The standard error is smaller still. And then once we get to 30, the standard error is smaller. The mean is really close to the true value. And we now have something that is approximately normal. So for this, that's what the central limit theorem states. The central limit theorem states that as sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like a normal distribution. And essentially, this is what the central limit theorem states. When the sample is large enough, the distribution of sample means is very close to an approximately normal distribution, no matter what the shape of the population distribution was, as long as the population has a finite standard deviation. So for us, you'll notice that it got better and better the closer we got to 30, and then once it was at 30, it was approximately normal. So the central limit theorem, numbers-wise, states that for large samples where n is greater than or equal to 30, x bar will be approximately normal. However, for small samples, the distribution of x bar will resemble the shape of the population. So essentially, you have to take a large enough sample size to get it to be approximately normal. Otherwise, it's just going to have the same shape that the population distribution did. Okay, so just to summarize that, the main theorems behind what we're going to be doing. The mean, the notation is mu, the standard deviation is, sigma divided by the square root of m. And the shape is approximately normal as long as the sample size is large. And the larger the distribution, the closer it is to normal. So again, just notation-wise, the distribution of x bar will be approximately normal, where the center is the mean, and the standard deviation is the standard deviation divided by the square root of your sample size. So what conditions need to be met for that to be true? They're very similar to proportions with just some slight differences. For the random condition, you still have to randomly sample or have a randomized experiment. The 10% condition is still true. You want to make your sample is less than 10 sample size is less than 10% of the population as a whole. And then where it's different, instead of having at least 10 successes and at least 10 failures, your sample size has to be greater than or equal to 30, or the population shape was normal anyway. So this only needs to be true if the population shape was not already normal, so like skewed left or skewed right or strong outliers. If it's already normal, it won't matter what the sample size is. But if it's not already normal, this will have to be true. Sample size will have to be bigger than or equal to 30. Okay, so let's look at an example. Wildlife scientists studying a certain species of frogs know that adults should weigh an average of 118 grams with a standard deviation of 14 grams. So if we were going to describe the sampling distribution about the mean weight of a random sample of 50 frogs, we would have to use those formulas. So if we're going to describe the sampling distribution, that means what's the shape and, what's the mean, what's the standard deviation. So for this shape, first off, since we're sampling 50 frogs, the central limit theorem tells me that it's going to be normal. So if it's normally distributed, if there's a normal shape to it, then I can use my formulas. And the mean is going to be equal to whatever the sample mean was. So, 118. For the standard deviation, remember the standard deviation, you have to take what it originally is and divide it by the square root of the sample size. So I would have to take 14 and divide it by the square root of 50, and that would get me 1.98 grams. So again, using the central limit theorem, this information must be true. And then we can use this information to answer some questions. So, for example, if you have a random sample of 50 adult frogs and it gives a mean weight of only 110 grams, is this unusually low? Okay, well, so for this, you're gonna have to use StatCrunch in the normal calculator because, as we already mentioned, this is normally distributed. So for this, is it unusually low? Well, find the probability of getting this value. So for this, I would go to Stat, I would go to Calculators and select the normal calculator. I know that the mean is 118, and I figured out on the previous screen that the mean standard deviation was 1.98. So I'm going to enter in 1.98. And then we're trying to figure out, is it unusually low to get 110 grams? Well, let's figure out the probability of getting something that's 110 or smaller. And if I do that, I get 0.00002. So think about what that's saying. That's saying that the probability of getting something that's less than 110 with this distribution is practically zero. So yes, this is unusually low because the probability of it occurring is practically 0%. Now let's look at what percent of similar samples would have an average weight of more than 120 grams. Okay, so now I just want to look at what's the probability of it being 121 or larger. So I can just switch my symbol to greater than and calculate 121. 0.06 is the decimal I get. So I would say roughly, let's say 6.5%. Just going through this to give you a reminder of how to work this normal calculator. What percent of samples is between 115 and 120? Well, for that, I could switch it to between. And we wanted to know the probability that it's between 115 and 120. If I compute that, I get 0.84, so 84%, I could say. And then what is the fifth percentile? So don't forget for percentile, I'm going to switch it back to standard. For the percentile, that's the percentage of everything that's at or less than that value. So for this one, I'm going to switch my inequality symbol to less than, and percentile is giving me the percent. So I would go over to this box here and type in 0.05, and if I click compute, that gets me 114.7. So I could say 115 if I round it. So just a reminder of, some of these questions, how some of these questions can be solved with the normal calculator on StatCrunch. Okay, and then the next screen has the answers there for you to look back on. Okay, so now let's look at actually constructing confidence intervals. For a confidence interval, things to think about. First off, we never actually know the standard deviation for the whole population, right? We can only estimate it. So when this happens, it's more natural to use S. Remember, S is the symbol for the standard deviation of the sample. So just a reminder, instead of actually using the standard deviation of the population that we don't know, we have to use the standard deviation of the sample. And so then we use that to estimate the standard deviation. And so remember, the estimate of the standard deviation is called the standard error. And so for us, the standard error is going to be the standard deviation of the sample size still divided by the square root of n. So just reminder of that. We never actually know this value, so we have to estimate it and actually use the standard error. Just a reminder of that vocabulary. And so this does cause an issue when we're working with means, because what ends up happening is this works well for large samples, but it doesn't end up working as well for small samples. And it turns out there's too much variation in standard deviation from sample to sample for it to work. So what ends up happening, I mentioned we're going to look at a new distribution. A statistician named Gossett recognized the need for models other than the normal model because that needed to change based on sample size. So a normal model, it turns out, is not as effective when you're working with means as other models are. So instead of looking at normal distributions when we're dealing with means, we're going to look at the t distribution. It's a new distribution. So when we don't know sigma, the standard deviation of the population, we can estimate it using the sample standard deviation S. But when we standardize based on the sample standard deviation, it turns out that the statistic has a new distribution called a t distribution. The t distribution has just a slightly different shape than the standard normal curve. It's still symmetric with a single peak. However, it has much more area in the tails. So again, the student's t-distribution is the solid curve here. The normal distribution is the dashed curve. So what ends up happening, just a comparison, they look really similar, but the t-distribution has more area in its tails than the normal distribution does. So, just trying to explain this a little bit more, because it's hard to wrap your brain around conceptually, especially for like a gen ed level statistics course. But he was doing an experiment on beer, and what he found was that the normal model was not accurate, especially for smaller sample size. It was still, the data that he was looking at was still bell-shaped, but certain details were different depending on sample size. So he came up with what's called the student's t-distribution, and it worked correctly. So for this, just some slight differences, but certain things are still going to be true. So with normal distributions, we looked at z-scores. Well, with t-distributions, we're still going to look at t-scores. And the formula is no different. We still take the observed value minus the mean and divide it by the standard deviation, in this case, standard error, because we're having to estimate it. And the only difference really is that since it changes based on sample size, the t-distribution has something that's new, and that's called degrees of freedom. And the degrees of freedom are equal to the sample size minus 1. And so I know this is going to be weird, it's going to be challenging to explain, but essentially for every sample size n, there is a slightly different shape for the t-distribution. And so it's categorized by its degrees of freedom. Just some notation, degrees of freedom are often abbreviated with DF. But again, the degrees of freedom that it has is equal to the sample size minus 1. And essentially, for like the definition of degrees of freedom, it's the number of independent quantities that are left after you've estimated the parameters. So I know that might sound funky, and if it helps to just kind of accept this and know that this is what we do, that's okay. But just to make a comparison, again, the density curves of t-distributions are similar to the normal curve. The spread is a little bit greater than that of the normal distribution, and it has more probability in its tails and less in the center compared to the standard normal curve. And as the degrees of freedom increase, the density curve approaches the standard normal curve ever more closely. So essentially what ends up happening is if you have a large enough sample size, it'll end up being approximately normal anyway, but you have to have a large enough sample size. So when we're calculating confidence intervals, you might recall from the last chapter that you use z-star, the critical z-values. When we're working with means, you're going to have to use the t-distribution, and you'll have to find critical t-values instead of z-values. It's going to work the same way. You'll still go to stat calculators. The only difference is now you're going to be selecting the t-calculator, and instead of just putting in the percentage, you'll have to also put in the degrees of freedom, which again is n minus 1. So for this, just an example, suppose you wanted to construct a 90% confidence interval for the mean of a population based on a simple random sample of size 10. What critical value for t should you use? Well, for this, just switching over to the StatCrunch calculator. And let's see if I can split screen this so I can still see my information. So for this, I want to construct a 90% confidence interval. So I'm going to go to stat and then calculators, t calculator, since I'm looking at means. Remember to find the t star, you switch it to between. And for the degrees of freedom, it said I'm doing this for a sample size of 10. Remember, the degrees of freedom is n minus 1, so I'm going to put in 9. And then it said 90% confidence interval, so I'm going to put 0.90. And so the critical t value would be 1.83. That's all you'd have to do to find that. For the next example, what if you wanted to construct a 99% confidence interval using a sample of size 75? Again, all that we would have to do for that is change this to 74 because it gave a sample size of 75, and then it said 99%. So just showing that again. So that would be 2.64. So it's really, really similar to what we were doing previously. You just have to make sure you use the t calculator instead of the normal calculator. Okay. So for the confidence interval, that definition has not changed. The name for it now, it's going to be a one sample t interval when you're doing means. So you're going to have to use t critical value. So it's a one sample t interval instead of a one sample z interval. The name one comes from the fact that it's a single survey question, and then mean is because we're looking at the average for a population. And so the formula really has not changed. You're going to take your sample statistic and add or subtract your margin of error. And for the margin of error, now it's going to be T star instead of Z star, and it's going to be the sample standard deviation divided by the square root of the sample size. So the idea of statistic plus or minus the margin of error, that has not changed. It's just you're going to be doing slightly different formulas and slightly different distributions when you're working with means as compared to proportions. So the conditions that need to be met, remember, you still have to be selecting randomly. The sample size still has to be less than 10% of the population size, and the sampling distribution must be approximately normal, which can be met by either the population is already normally shaped or the sample size is greater than or equal to 30. Or the graph of sample data has no strong outliers. So sampling distribution being approximately normal can be satisfied by any one of these three things. And just a reminder of the notation, and we do these things because it gets an approximately normal shape, it gets an unbiased measure of center, and it allows us to actually be able to calculate the standard deviation. Okay, so when you're using StatCrunch to get your confidence interval, it's going to look really similar to proportions. The only difference is instead of going to proportion stats, you'll be going to t-stats. We're still looking at one sample, and then typically you're going to select with summary. I am going to show you an example of one where you do it with data. Okay, and the interpretation is not going to change. We're still going to be saying we are blank percent confident that the interval from blank to blank captures the true mean or whatever we're looking at. Okay, so let's look at an example. 194 is a busy highway that passes through a residential neighborhood and two school zones. Residents there are concerned that vehicles often exceed the posted speed limit in the school zones, which is 35 miles per hour. The local police sometimes place a radar speed detector by the side of the road. As a vehicle approaches, this detector displays the vehicle's speed to its driver. The police hope that drivers will slow down if they are reminded of their speed. The speeds that were displayed on the radar during one 15-minute period on a certain weekday, 50 vehicles were observed with an average speed of 39.5 miles per hour and a standard deviation of 3.4 miles per hour. So with that information, again, I'm just restating the summary. We're going to find and interpret a 90% confidence interval for the mean speed of all vehicles traveling on 194 on a weekday. Okay, so to do that, I'm going to go to StatCrunch and I'm going to set it to where I can see my information at the same time. And to get the confidence interval, I have to go to Stat, T-stats, because I'm looking at a mean, one sample, and then, of course, it's getting cut off with summary. Okay, so the sample mean, it said that the average speed was 39.5. The sample standard deviation was 3.4. And the sample size, it said 50 vehicles were observed. And then I'm just going to click confidence interval and put in 0.90 because that's the percent it gave me. And if I click compute, did I accidentally click cancel? Let's see. Stat, T-stats, one sample with summary, 39.5, 3.4, 50. Oh, I did accidentally click cancel. That sucked. And then compute. Okay, so here we go. And there's my confidence interval, 38.7 to 40.3. So really, it truly is the same steps. You just have to make sure you click on the right things, when you're doing proportions versus means. So remember, we would say we are 90% confident that the true mean speed of cars that travel on 194 during the weekdays is between 38.7 and 40.3 miles per hour. Okay, so I want to look at an example because sometimes with means they like to give the raw data. So a coffee machine dispenses coffee into paper cups. The machine says that it dispenses 10 ounces, but the actual amount varies from cup to cup. So here are the actual amounts for 20 cups. Is there evidence that the machine is shortchanging customers per a confidence interval? Okay, so if it gives you a list of data rather than a summary, you will typically have to enter the data. I went ahead and entered it for us, but you would have to enter the raw data, And then the only thing that changes for calculating a confidence interval, when you go to stats, t-stats, one sample, you're going to want to pick with data. If you don't have the summary information and you have the raw data, that's the only time that you would click with data. And then in that case, you would just select the column that the data is in and then select confidence interval. And for this one, it doesn't specify confidence interval, so I'm going to leave it for the default of 0.95 and click compute. Oh my God, did I click cancel again? Lord help me. Let me see. With data, coffee ounces, confidence interval, compute. What the heck? Oh my gosh, it's just way over here. Okay, so then my confidence interval, 9.75 to 9.93. Okay, so are they shortchanging people? It says that it dispenses 10 ounces, but the confidence interval tells me that it has anywhere from 9.75 to 9.93 ounces on average. Since 10 is not in that interval, it means it's not a plausible value. So I would say that there is evidence that they're shortchanging people because 10's not even a plausible value. Okay, so one last topic to kind of close out this video with, and that is bootstrapping. So sometimes all we have is a sample that we expect is representative. There is a computer-intensive method of creating a confidence interval for the mean from a single sample. So remember, the whole idea of confidence intervals is we take many, many different samples and construct intervals off of those. Well, sometimes you only have a single sample. And what bootstrapping does, it essentially allows us to create confidence intervals when you have just a single sample. And what it does is it takes appropriate percentiles from a bootstrap distribution and it calculates reasonable confidence intervals for a mean from that single samples. And you do this when the assumptions for a t distribution are not met. And so in sampling, you don't have a population. If we did, we wouldn't have to sample. When we only have a sample, we rely on this powerful central limit theorem to tell us about the sampling distribution for reasonable sample sizes. We then use that theorem to build confidence intervals for the mean. But it turns out that there's a way to approach this problem that relies on the power of modern computers to essentially simplify the process for us. And so the basic idea, we don't have the population, but we do have a sample. The sample is supposed to be representative. So what if we make lots of copies of this sample, build a pseudo population, and then sample repeatedly from that population? As before, we're still going to find the means of our samples and collect these means in a histogram. From the histogram, you'll see how the sample means are distributed, and more importantly, how much they vary. So for bootstrapping, the limits propose a 95% bootstrap confidence interval for the population mean. We might say that we have 95% confidence that this interval includes the true mean. Notice that we said a 95% confidence interval and not the 95% confidence interval. If we drew bootstrap samples again, we'd get different bootstrap means and a slightly different interval. You and your classmates would get different bootstrap confidence interval even if you use the same data because the computer is just generating it. So for this one, if you look at a bootstrap confidence interval compared to the intervals for coffee, so we had a 95% confidence interval for the mean of the coffee that was 9.75 and 9.94. So if we bootstrap that data, we'll need the 2.5% and the 97.5% percentiles. And again, to get those, I would just have to put that in the calculator on StatCrunch and it'll tell me what percent of data falls below those values. So you would have to find the percentiles, which for 9.75 was 2.5% and 9.94 was 97.5%. To do a bootstrap, the steps for it, and there's just like one or two homework problems on this. You would have to go to stat, resample, select statistic, and you would select the column that had the raw data. And again, it'll show you the steps in here. And when you do that, this is the information that you should get. So for this, I'll just like show it with my coffee data real quick. And I'll have the steps pulled up here just so you can follow. So again, I'd go to stat, we go to resample statistic, pick the column that has the data, and then build the mean column. Oh, hold on, I forgot to select something. Oh, 999 samples works better than oh, I'm not clicking something right. Okay, I forgot to click something. Let me see. Stat resample statistic. Select your column. You have to build the mean column. So if you click build, clicking when you're building a function in StatCrunch, it's really picky about what you click. This is what I forgot. I forgot to do build. I'm in the habit of just, doing calculate. So you have to click mean for the expression, and you have to click mean and then add function. And then you have to click the column that you want it to select to calculate the mean of and click add column. And then if you close parentheses and click OK, you have to make sure that you store the statistics in the data table. And for StatCrunch, 999 samples resamples seems to work better than 1,000. So if you click your column, build the mean of that column, put in 999 samples, make sure that you store the resampled statistics in the data table, and click compute. It will automatically store the resampling in the column next to the original column. And so then building the confidence interval off of that, you would have to do stat, calculators, T calculator. And when you select that and do one sample, or excuse me, stats, T stats, one sample with data, we still have raw data, but now let's look at it when we just do the mean of the coffee ounces and not from just our one sample, and you click compute. For this, it has, oh my gosh, StatCrunch, you're ticking me off today. T-stats, one sample with data, mean, confidence interval, compute. When I do that, let me move it over here. I get 9.84 and 9.84 to 9.84. So that's what I got. If you ran this, you might get different numbers. Like when I ran this earlier, I got 9.75 to 9.93. So it just truly depends. Like it's random and it's regenerating it. So, but it will get something that's close to what really happened. So just things to be careful of. Don't confuse proportions with means. Beware of multimodality. If a histogram is not unimodal, consider separating it into groups and analyzing each group separately. Set outliers aside. Outliers violate the nearly normal condition. So sometimes if it's better, take those out of the data set and then do your calculations. But then, of course, you'd want to make a statement that you excluded it. And then watch out for bias. Even a large sample size cannot save you if you sampled in a biased manner. Make sure that your conditions are met, and then interpret your confidence interval correctly. Make sure the confidence interval is about the mean of the population and never about the samples or individuals in the population. Okay, so let me know if you have any questions after watching, and you should be able to complete the Chapter 17 homework now.